My name is Mahi Mithagiri. This is a computer vision project done together with Gautam. In our project, we are reconstructing images from deep CNN feature maps using a lightweight decoder. In simple terms, instead of starting from raw pixels, we start from intermediate features extracted by a deep network, and then we try to invert them back to an original image. This helps us to understand what information is preserved in these intermediary representations and how much of the original image we can recover. So let's start. Next slide. So this is our project overview. In this project, our main goal is to reconstruct face images from deep CNN feature maps using a small and efficient and decoder. To begin with the high level pipeline, we take an input image, we pass it through a pre-trained encoder to get the feature maps, and we use a lightweight decoder network to reconstruct the images from these feature maps. So we then evaluate how closely we can reconstruct these images to originals, both numerically and visually. Next slide. So this is the data sets we used. It's a CELB high quality data set. So it contains about 30,000 high quality facial images. The original dimensions are 1024 times by 1024. For this project, we have reduced them to 224 times 224 by 224 resolution. So this data set is one of the widely used for face generation and reconstruction tasks. So it is a good fit for our encoder and decoder model. So we train the model to reconstruct these face images from their feature maps and then test on held out samples to see how well it generalizes. So next slide. So let's start with the motivation. So the motivation behind this project is mainly interpretability and efficiency. First we talk about the image to feature reconstruction is closely related to interpretability. It lets us see how much information intermediate feature maps retain, and also it provides intuition about what the model encodes at different depths of the network. Second, we have a small decoder parts. That is, they are more suitable for low resolution development. They help with privacy analysis. For example, how much can be reconstructed if only features are shared instead of raw images. And the third one is educational settings, where hardware, when they are also useful in educational settings where the hardware is limited, but still we want to demonstrate feature emotion and reconstruction. So this is about my part. Now my friend and teammate Gautam will explain the architecture and continue. Thank you.
Hello everyone, I'm Gautam. So we are in the slide discuss about architecture encoder. So on the left hand side we can see the architecture diagram for the encoder. So as we see, image reconstruction system goes through frozen encoder, then it goes through feature map, then it goes through decoder, upsample and output, and we get the reconstructed image. So coming to encoder part. So on encoder side we use a frozen encoder network. Its job is to extract feature maps from the input image. The encoder outputs 56 by 56 by 256 tensors, which serves as the input to our decoder. Importantly, the encoder is not trainable during reconstruction. It's frozen. This means we are not changing the feature representation itself. We are only training the decoder to interpret those features and reconstruct the image. That isolates the reconstruction ability of the decoder. Then coming to decoder. The decoder is where all the learning happens. We design a lightweight decoder composed of upsampling layers to gradually scale the feature maps back up to the original 224 by 224 resolution. Convolution 2D layers with residual blocks, which helps the network captures spatial structure and refine details. The final output is a 224 by 224 reconstructed image. The overall goal is to keep the decoder small and efficient while still being powerful enough to recover meaningful structure from the feature maps. Then uh, coming to training pipeline. For training, we used a combined SSIM plus L1 loss. So what are these? So SSIM focuses on structural similarity between the original and reconstructed image. Coming to L1 loss encourages pixel level accuracy and stability. We train with the Adam optimizer and run over the full dataset for each epoch. It mostly at 3, 3725 batches per an epoch. So coming to the pipeline, take a batch of real images from Celeb HQ dataset, pass them through the frozen encoder to get feature maps. Feed those features into the decoder to get reconstructed images. And after that, compute SSIM plus L1 loss between originals and reconstructions. Backpropagate and update only the decoder weights. So we are done with the training part. So coming to the evaluation metrics. So to evaluate reconstruction quality, we use both quantitative metrics and visual inspection. The main quantitative metrics are mean square error to measure average pixel-wise error. So coming to peak signal to noise ratio, a standard image reconstruction metric. So coming to SSIM, structural similarity index, which assess perceptual quality. Along with these metrics, we also look at visual comparisons between original and reconstructed image to see how well identity structure and facial details are preserved. So as we look at in the slide, this is the sample evaluation image as you see within original and reconstruction. So we can see the mean square error, PSNR, and SSIM values on the top. Coming to plotting. So as we see here, there are three kinds of plots we used in our project. So coming first, let's discuss about PSNR distribution. So most of the reconstructed image fall between 22 and 25 decibels, which shows that the model consistency preserves a good amount of pixel level details. A few images go beyond 26 decibels, usually when the face is similar or less textured. When we look at the sample reconstruction, you can see the decoder does a solid job capturing overall facial structure, skin tone, and lighting. It doesn't perfectly recover sharp details like hair or texture, but identity and major features are clearly maintained. The SSM values, mostly between 0.70 and zero point 0.8, uh, confirm that the structural similarity remains strong across the datasets. Looking at SSIM distribution also reflects this consistency, with most images clustering in the same range and only a few outliers for more challenging examples. Finally, if we look at it, the training loss curve shows smooth, stable convergence, meaning the model learned the mapping from features to images without overfitting or instability. Overall, these results show that mid-level convolution neural network features contain enough information for a lightweight decoder to reconstruct faces with reliable structural and fidelity, even if fine details aren't perfect. Coming to sample test images. As we discussed before slide, so for SSIM and PSNR distribution, so as we see in the uh, slide here, so the image reconstruction is almost the same, but as we discussed before, it is quite difficult for hair and textures because of lightning. So as we see, we have four images here and with mean square error, PSNR, SSAM values. So let's move on to the next slide. Coming to results and visualizations. Here are show test samples as we've seen before and the corresponding reconstructions. The results demonstrate that decoder learns meaningful structure from the feature maps. Reconstruction captures the semantic content, for example, face layout, hair, and overall identity cues. As you see here, that's a thing. So then moving forward, at the same time, there are some blurring which is expected given the small size of the decoder and the information loss in intermediate features. Overall, the model strikes a reasonable balance between compactness and reconstruction quality, especially for a lightweight architecture. Then coming to the conclusion and the future work. To conclude, we showed that the small decoder can still be effective for reconstructing images from the deep convolution neural network feature maps. This supports the idea that intermediate convolution neural networks features retain rich spatial and semantic information even when the decoder capacity is limited. For future work, there are several directions. Using the deeper or more expressive decoder architecture to sharpen fine details, incorporating perfectual loss functions or adversarial losses to improve visual realism, exploring different encoder depths to study how much information to retain and various layers. Thank you for everyone. As we're done with the coding presentation, let's go to the code. So this is our code. Let's so before train the model, we have to extract the features. So let's extract the features. So it's gonna take some time as there are 30,000 images. So it has to create batches for those 30,000 images. So let's wait for that. As you see, we are already near to the 30,000 images. Let's wait for some time. We are done with the extraction. So why we are extracting the images? So because extracting each and every image from the 30,000 images and reconstruct and train them, it is very difficult and it's gonna take so much of memory usage and so much of time. So because of that, we are extracting images first from the all the 30,000 images, so it will be easier to train. So after extracting images, the next part would be, of course, the to train the model. So let's train it. We can see the architecture. So as we see, there are 3,750 steps, which are 3,750 batches. So among these batches, there are 30,000 images. So we are hovering through, like moving through all the 30,000 images for each epoch. So it will be 30 epochs. For each epoch, it will be hovering through all 30,000 images. So it will take quite some time. So as we see here, it will be taking like 8 minutes per an epoch. So it will be like 8 minutes into 30 epochs. While we wait for that, we already trained the model. So let's skip this part. So let's test the model. As you see, it got the testing is completed. As you see, the reconstruction matrix per batch average. So we can see mean square error, PSNR, and SSIM. And we can see some comparisons as well. So let's go to that file and test the comparisons. So as we see here, the original and the reconstructed image. Let's go to another image. And the same for original and reconstructed. And the same for original and reconstructed. And the same thing. So let's evaluate the model. As is done extracting, training, and testing the model, let's evaluate with the sample images. As you see, it has completed evaluation for 200 samples. Let's go to the results and check the evaluation. So this is evaluation. Let's look at the histogram. So we can see the PSNR distribution. Then let's go to the sample reconstructions. These are from the 200 samples, these are 4 images which are outlined here. So as we see original on the top, reconstructed on the bottom, and we can see mean square error, PSNR, and SSN values in the middle. So we can see the reconstruction is pretty uh, like original. So there are some features which need to be reconstructed, like hair and the textures and the lighting as well. So as we are using the small decoder, so this is the result. For the better results, we have to use, like as we discussed in the presentation, we need more depth decoders. Let's look at SSIM distribution. So this is the one. Let's look at the curve. So we can see training loss curve. So let's look at the front end. So how it's gonna look. So this is our front end dashboard. So as we see here on the left hand side, we have option to image upload and webcam. So we are also using the webcam. So it will take live images from the webcam, and for each frame, it will try to convert to the reconstruction from the original image. So on the right hand side, we have an upload button. So to upload the images to get the result, let's test for webcam. So we can select a webcam. Let's start it. Hello. So this is my webcam. So as we see, the original image is converted to frames, and each frame is getting reconstructed based on the decoder weights to the model. So as we see, the texture is not good because of the lighting. So as we are using small decoder, the textures, we cannot recognize the textures well, and the hair and the body. So this is our result. Thank you, everyone. Thank you for listening.